Look at the chlorine atom. It has 17 protons and 17 electrons. So since it has equal numbers of positively and negatively charged subatomic particles, it is considered to be an atom and it has no charge. For the chlorine atom to be stable, it needs to gain one electron. And if it actually gains that electron, not by sharing, but by stripping it away from another atom, it is no longer called an atom, it is called an ion. So you can see here this chlorine atom has gained one electron. So now it has 17 positive charges, 18 negative charges, an overall total of one negative charge. So it is considered to be a negatively charged ion or an anion. Here we see our sodium atom with 11 protons and 11 electrons. 11 protons are 11 positive charges and 11 electrons are 11 negative charges. So overall those charges cancel out, giving the sodium atom no overall charge. That sodium atom to become stable is either going to have to gain 7 electrons to have 8 in that second shell, or it's going to lose 1 electron. It's more energy efficient for it to lose 1 than to gain 7. So it loses 1. Its stability drops down to the second shell, and on the second shell it has 8 electrons. So now a total of 10 electrons, if you add the 8 electrons from the second shell and the 2 from the first shell, and sodium having 11 protons, you end up with an overall positive charge of 1. So sodium is now considered to be an ion, and in reality it's called a cation because it's positively charged. So now we have our sodium ion of 1 plus charge, our chlorine ion of 1 negative charge. They can be held together through what's called an ionic bond. And an ionic bond is where you have a transfer of electrons. So that electron that sodium lost was gained by chlorine. So there's different ways to represent molecules. You can represent them by naming, like for example, water. You can represent them by a more complicated naming system, such as a chemical naming formula, which is called nomenclature, such as dihydrogen monoxide, which is very descriptive in that it's composed of 2 hydrogen atoms and 1 oxygen atom. You can represent with a structural formula, which you can see are the letters of the elements of the atoms, 1 O and 2 H's, with the lines being bonds or sharing of electrons between the oxygen and each hydrogen. Or you can represent by a structural model which tries to show the relative sizes and positions of the atoms. Since hydrogen only has 1 electron, it's represented to be smaller than oxygen. And then the shell model, which is showing you basically what we just reviewed, how all of the electrons interact with all of the different atoms. So in the shell model, you can see the oxygen centrally located with 2 electrons on its first shell and 8 on its second shell. And it became stable with 8 because it's sharing 1 from each hydrogen. And the hydrogens are now stable on their first shell because they're sharing 1 electron each with oxygen. So going back to our sodium chloride, since the sodium lost an electron and the chlorine ion gained it, we can form what's called a crystalline lattice. And we can see this represented by the purple and green spheres. And the sodium and the chlorine basically surround each other, and their positive and negative charges attract in ionic bondings. So it forms a really rigid solid structure. But this rigid solid structure can be decomposed, which we'll get to in a minute with hydrogen bonding in water. So here's another view of an ionic bond. It's basically a force between the 2 ions when the electron is transferred. Again, the sodium being 1 positive and the chloride being 1 negative. That forms an attraction of opposite charges, which holds the 2 ions together in the lattice. Now, besides ionic bonding, there is covalent bonding. And covalent bonding comes in 2 forms, polar and nonpolar covalent bonding. Nonpolar covalent bonding is where the two electrons that are being, or excuse me, the two atoms that are being shared in the covalent bond are, in essence, very similar or the same. For example, in this picture we see molecular hydrogen. It's made up of two hydrogen atoms, and each hydrogen atom has one proton and one electron, and they share that one electron, and that means their first shell becomes stable with two electrons. It's nonpolar because since they're identical atoms, they each have equal pull on the electrons that they're sharing. Same thing in the second image with molecular oxygen. We have two oxygen atoms being held together. Each one has two electrons on their first shell, and now they're stable with 8 electrons on their second shell. And they're stable with those 8 electrons on their second shell because they're sharing a total of 4 electrons or 2 pairs. This is called a double bond or a double covalent bond. One covalent bond is where two atoms share one pair of electrons. If two atoms are sharing more than one pair of electrons, it's considered to be a double bond. And then in our last view, we see water molecule. Now you can see the atoms that make up the water molecule are very different. Oxygen is much larger than each hydrogen, and oxygen is more what's called electronegative, which means it's a stronger atom and it can hold or pull electrons towards it more strongly than the hydrogens can. So although each atom involved in the water molecule are stable, each hydrogen with 2 electrons on their first shell, and the oxygen with 8 electrons on its second shell, so they are all stable. This is not considered to be a nonpolar covalent bond between each oxygen and each hydrogen. It's actually considered to be a polar covalent bond, with the oxygen having the electrons spend more time with it than each hydrogen. So each hydrogen has a slight positive charge, whereas each, or the only, oxygen has a negative charge. And that's what gives water a lot of its dynamic properties, and one of those properties is the ability to form hydrogen bonds. Now, a hydrogen bond is not drawn by a solid line because it is not an actual transfer or sharing of electrons. It is an interaction of molecules based upon attraction of opposite charges. So since each hydrogen in a water molecule has a slightly positive charge and the oxygen has slight negative charges, a hydrogen bond can form between them. Individually, hydrogen bonds are very weak, but collectively they are very strong. In fact, they are what hold DNA together. So DNA is made up of 2 double-stranded molecules, and each one of those strands are held together by multiple hydrogen bonds. Again, individually they are very weak, but collectively they are very, very strong. So just to review, water is a polar molecule because it is made up of 1 part oxygen and 2 part hydrogens held together by polar covalent bonds. That creates a slight negative charge on the oxygen and slight positive charges on the hydrogens. So that then means water molecules, which you can see here, there's several of them, are able to be held together by weak hydrogen bonds.